Okay, in this video we're going to talk about multiple regression, and we're going to derive the formulas for the least squares estimates for multiple regression. So in least squares for linear regression, what you're given is, so you're given a bunch of data points, x1, y1 to xn, yn, and you want to find the best fit line. The best fitting line that captures the data in some sense. And in the least squares approach, so in the least squares approach, what you're looking for is you want m and b, so your slope and the y-intercept, that minimize the sum of the squares of the residuals. So that would be y1 minus mx1 plus b. So mx1 plus b is in parentheses, right? That's your estimated y value. You subtract the y value, you square them, you square it, and then you sum up over all the y values. And so this can be rewritten as, see, if you take, let's see, if you take this vector, which is y1 to yn, and you subtract, so you take this matrix, which is all ones, and then x1 to xn, and then multiply it by by bm. Okay. So each of the components are yi minus b plus mxi, right? So you're trying to minimize the magnitude of this vector. That's the magnitude of that vector. And let's call this matrix A, and let's call this matrix beta, so that column vector, and then this would be y, right? So you're trying to minimize, you're trying to find a vector beta that minimizes the length of y minus a beta. That's what you're doing in least squares, okay? And in a previous video, I explained how to use the concepts of orthogonality and projection to calculate that vector. You basically want to project the vector y onto the column space of A, and that vector is what you would use. Okay, so as your y hat. Okay, and in this video, we are going to talk about a way to do this using calculus. And in a previous video, I explained how to do this using a multivariable calculus, but only for a line, right? And this time, well, in the previous video also, in another video, I explained how to do this in general, just when you have a general matrix A. And that's what we're going to do in this video with multivariable calculus. So in multiple regression, what you're given is you might have x1 to xn x11 to x1n y1, and then all the way to x1, let's see, xm1 to xmn ym. So you might be given m data points, and then you want to find, so you want to minimize y1 minus the x11 beta 1 plus dot 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 plus x1n beta n, that squared, all the way to ym minus xm1 beta 1 plus dot 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 plus xmn beta n squared. So that's a function of beta 1 through beta n, and you're trying to minimize those. So in this case, you're given m data points, but your data points, your y's are functions of n different variables, and you're trying to find the linear function of those, of the n variables that gives you the closest approximation to the data. Okay, so again, this is a residual sum of squares, right? You're taking the sum of the squares of the residuals, and you are trying to minimize them. All right, so this is a function of multiple variables, n variables, and oh, before we go on, I should say that, well, what about the intercept? Okay, so the intercept you can just take to be beta 1, and then you can set your x11 to 1. Your x11 and your x21 all the way to xm1 equal to 1. So if you take x11 to be x21 all the way to xm1 to be 1, then you can interpret beta 1 as the analog of the y-intercept except for a plane. So as the intercept. Okay, I guess I'll call it the y-intercept. But it's, you know, y is the independent variable, right? Okay. So I'll put this in quotes. Okay, so in this case, so how does this connect with what we had before? So this is when, so just to connect it with what we had before, what we're saying is that this is, B would be our beta 1, and would be our beta 2, and this A is your x11, x21 to xn1, x12, x22, all the way to x, oh, this is M, and then M2. So that's the connection here. So in this previous example, we had n, let's see, yeah, n data points, but in this scenario, we have m. So what we have is, so we're trying to minimize the length of the vector, which is if you take your y1 to ym and then subtract this matrix whose entries are xi, so x11 to x1n to xm1 to xmn times beta 1 to beta n. So let's call that matrix A, let's call that matrix beta, let's call that matrix Y. So you're trying to minimize, you're trying to choose this beta. So you're trying to choose this beta because you're given your A and you're given the Y, and you want to choose the beta that minimizes the length of this vector. Okay, so that's what you're doing in least squares in multiple regression. Okay, so now we're ready to take the partial derivatives. So remember that when you have a function of several variables that's differentiable, this is differentiable, and you want to maximize it or minimize it, in this case we want to minimize, you take the partial derivatives with respect to the independent. Oh, sorry. What I said before was that y was the independent variable. I mean the dependent variable. Right? Okay, so you take the partial derivatives with respect to the independent variables. So in this case, they're beta 1 to beta n. You set them equal to 0. And then you have to check that what you have is actually a minimum. Okay, so this is actually for a local minimum. But the idea is that when you only have one local minimum, I mean, in this case, we're going to see that the local minimum is actually a global minimum. So you don't have these issues where, okay, you might have a function that has the local minimum, but it's not actually the global minimum. In this case, the local minimum is the global minimum. And we'll see that. So how do we do this? We will take the partial derivatives of this function. Okay. So let's take the partial derivative with respect to beta 1. So if you do that, you're going to get 2 times y1 minus x11 beta 1 plus dot 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 plus x1n beta n times negative x11. Okay. That is from the derivative of the first term, because you bring the 2 down, but then there's a chain rule, right? You have to multiply by the x11. Okay, so that's the partial derivative of the first term, right? That's the partial derivative of the first term, but then you have to do all the other terms and then the last term, right? All the other terms. So you're going to get that and then plus 2 times y1 minus are you going to get y1? I think you're going to get y2, right? y2 minus x21 beta 1 plus dot 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 plus x2n beta n times negative x21. Okay, why is that? Because this second term is going to be y2, right? The second term is going to be y2 minus, if you look up here, where is it? If you look, down here, right? It's the second equation. You're going to get y2 is, x21 beta 1 plus dot 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 plus x2n beta n, right? So it's that squared. That's the second term. So then when you take the partial derivatives with respect to beta 1, you bring the 2 down, and then you multiply by negative x21, which is what I have here. And then you keep going until you get to m, right? So ym minus xm1 beta 1 plus dot 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 plus xmn beta n times negative xm1. Now if you think about, so that's the first partial derivative. Now if you think about what happens for the other ones, in general, if you take the ith partial derivative, you're going to get so if you take the ith partial derivative, okay, let's imagine taking the second partial derivative. So with respect to beta 2. So you're going to have the 2 comes down, and then you're going to have an x12, right? And then you're going to have an x22 for the next one. So basically the partial derivative in general, the ith partial derivative is going to be 2 times y1 minus x11 beta 1 plus dot 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 plus x1n beta n times negative x1i plus dot 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 plus 2 times ym minus xm1 beta 1 plus dot 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 plus xmn beta n times negative xmi. Okay, so you set this equal to 0 to find the critical points. Now I'm going to rewrite this equation. So first of all, we can divide everything by 2. So if you divide everything by 2, I can write this first equation as, okay, let's look at the partial derivative with respect to beta 1. So I can write this as negative x11 y1 plus x11 times x11 beta 1 plus dot 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 plus x1n beta n plus negative x21 y2 plus x21 x21 beta 1 plus dot 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 plus x2n beta n. Plus dot 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 minus xm1 ym plus xm1 xm1 beta 1 plus dot 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 plus xmn beta n. So that equals 0, right? That's the first partial derivative. And if you take this term with the negatives and move it over, we can rewrite this equation as x11 beta 1 plus dot 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 plus x1n beta n plus dot 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 plus xm1 beta 1 plus dot 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 plus xmn beta n equals x11 y1 plus x21 y2 plus dot 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 plus xm1 ym. Okay. Now this I can rewrite as, if I take this vector x11 x21 to xm1 times this matrix A times beta 1 to beta n equals x11 to xm1 to y1 to ym. Right? Because like this first one, that's just what I get when I take the dot product of the first row of your matrix A by the vector beta. And then the last number here is what I get when I take the dot product of this with beta. And then I have these x11 to xm1, that's here. So you can check that when you take this first thing, this is just equal to this. Okay. And then this term is just the dot product, right? That's this matrix product. So these two are the same, these two are the same. And so this is the equation I get by setting the first derivative equal to 0. And in general, for the ith derivative equal to 0, so notice that this row vector, that's the first column, that's the transpose of the first column of A. So this is the matrix A, right? I'm taking the first column first column is x11 to xm1, and then writing it as a row vector. So that's the transpose of the column. So in general, the ith, if you do it for the ith partial derivative, you're going to get the transpose of the ith column. Okay. So if you kind of put it all together, okay, you can rewrite this system. You're going to get a system of equations. You get one equation for each partial derivative, right? And so this first equation involves the first column, and then the second equation with the second partial derivative involves the second column of A, and so on up to all of your m columns. So one way to rewrite that is that I have, so the system of equations you get is, if you put it all together, it's x11, x21 to xm1, and then all the way to xn1 to xnm, and then times A, and then times beta 1 to beta n equals this matrix times y1 to ym. Well, that matrix here, that is just the transpose, right? That's just A transpose. So now the system we get is A transpose A beta equals A transpose Y. Those are the normal equations we found using linear algebra. So if A transpose A is invertible, that turns out to be, if A transpose A is invertible, then our beta is just going to be A transpose A inverse A transpose Y. And it turns out that, so the thing is that A is in general not a square matrix, right? So it's not about A being invertible, but A transpose A is a square matrix. Because if that matrix is invertible, then you can multiply by the inverse and solve for beta. Okay, and A transpose A will be invertible as long as A has linearly independent columns. So A transpose A is invertible if and only if A has linearly independent columns. Okay. I think that's like a linear algebra exercise. But you can find it in, if you want a reference for this, you can look in Lay's linear algebra textbook. So see the linear algebra and its applications by Lay, if you want to see a proof of this. Or you could try proving it yourself. I don't think it's that hard to prove. Okay. So that is the multivariable calculus way to derive this formula. The one thing we haven't checked is that that you actually have a minimum and not a maximum or a saddle point, right? So, and we have to check that we actually have a global minimum. So we only have one local minimum. Well, the idea is if you look at the partial derivatives, we have to look at the second partial derivatives, right? Because we're using the second derivative test. So it turns out that, okay, I'm just going to do some simple computations. So let's say that we wanted to find the second partial derivative with respect to beta 1 and then beta 2. Okay. So we take our first partial derivative, right, with respect to beta 1, and then we have to take the derivative of this with respect to beta 2. So what's going to happen is, let's see. Oh yeah, okay, so for the first term, so I have this x12 beta 2. So when I take the partial derivative, okay, I'm going to get an x12 here. So I'm taking the partial derivative of this with respect to beta 2. I'm going to get an x12, but then I'm going to have an x11 here. And the minus in front of the x11 will cancel with this minus here. So I'm going to get x11, x12 from this term, and then for the second term, so I'm going to get plus, and then I'm going to get x21, and then this is an x22, right? So I'm going to get x21 times x22, and then I'm going to get, the last one, I'm going to get an xm1, and then times, there's an xm2 here. So my second partial derivative, if I do partial with respect to beta 1 and then that with respect to beta 2, I will get x11, x12 plus x21, x22 plus dot 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 plus xm1, xm2. And in general, the partial derivative with respect to beta 1 and then with respect to beta 2 is going to be x1i x1j plus x2i x2j plus dot 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 plus xmi xmj. Well, I can write that as a matrix product x1i, x2i to xmi times the matrix x1j, x2j up to xmj. Well, this matrix, this vector is the jth column vector of A. And this matrix is the transpose of the ith column of A. Right? So I have a matrix. So I have a matrix whose ith j entry is this. Oops. This matrix, the ij entry, is the transpose of the ith column of A times the jth column vector of A. Well, that is just the ij entry of A transpose A. Because when I take A transpose A, the ith row of A transpose is the ith column of A. Right? So yeah, and then to get the ij entry, you take the ith row of A transpose and multiply by the jth column of A. So that's what I'm doing here. And so that means that the second partial derivative matrix is just equal to A transpose A. Okay, it's just A transpose A. So how do I know that I have a local minimum? I need all the eigenvalues to be positive. Now it's possible that some of the eigenvalues are 0, but the point is that this is a positive semi-definite matrix. Right? And we know that when you have a positive semi-definite matrix, that this matrix has eigenvalues that are either 0 or positive. So it doesn't have any negative eigenvalues. And therefore, you have to get a local minimum. Right. So that explains why you have a local minimum. And why do you have a global minimum? Well, because there's only one critical point, and you have a differentiable function. Now, is that enough to give you a global minimum? I mean, in terms of this function, yeah, you have a positive definite matrix everywhere. Yeah. The thing is that this matrix is positive definite everywhere, right? Independent of your beta. So it's not just that you have, this is like if you have a function that's concave up everywhere, basically. Then your minimum is a global minimum. So that's exactly what's going on here. So you have a global minimum. Yeah, so that explains why this is actually a minimum value of the entire function. So what did we conclude from this kind of long computation? So we saw that the beta i's, what we choose for beta i's, is a solution to the system of equations A transpose A beta equals A transpose Y. So if A transpose A is invertible, then you get this result. A transpose A inverse, A transpose Y. And we saw this using linear algebra before, so this isn't a new result. But what is new is the method. And actually, there are modifications of this least squares regression. There's something called ridge regression, which is sort of like what we did here, except a little different. And if you want to do the same method, the linear algebra technique doesn't work well. So it's actually good to know the multivariable calculus technique for this. And I plan to make a video where I go over this ridge regression and talk about the math behind it. So this is a method that's worth knowing. It's the second derivative test, right? The first derivatives, the critical points give you the critical points, and then the second derivative test classifies as a maximum or minimum. And then what's nice about this is that you get matrix, and all of the mathematics boils down to matrix computations when you write it out correctly. Okay, so a fairly complicated computation, but it's still a good one to know. Okay, thanks.